Lecture of physico-chemical aspects of biochemistry, titration curve. In this lecture, we will determine that how amino acid act as a buffer and they donate and accept hydrogen. It is used to demonstrate the buffer action of amino acid, and it is produced by monitoring the pH of given volume of sample solution after successive addition of acid or alkali. The curves are usually plot of pH against the volume of titrant added, or more currently against the number of equivalent added per mole of the sample of the weak acid or the amino acid. For example, here for the titration curve, we are taking the example of acetic acid, which is slightly dissociated into conjugated base and a proton. So we are taking the example of acetic acid. A strong base is added. This is the weak acid. Then we add the strong base such as sodium hydroxide. The acid is converted to its conjugated base into acetate ion. At the mid of the titration, where pH is equal to pK, the concentration of acid and the conjugated base are equal, or the dissociated and undissociated form are equal. At the end point, the conjugated base predominate. All the acid, acetic acid, is converted into acetate, and the total amount of hydroxyl ion added is equivalent to the amount of acid that was present in the starting value. Can be obtained from the titration data by the following method. The pH at the point of the inflection is the pK value, and this may be read directly. By definition, the pK value is equal to the pH at which the acid is half titrated, or the pH at which the acid is half converted into conjugated base, or converted into acetic acid and acetate and acetic acid are in half concentration. 50% is acetic acid and 50% is acetate. The pK can therefore be obtained from the knowledge of the endpoint. uh, Titration of the acetic acid. Here we are plotting the volume of sodium hydroxide added, and at that point we are plotting the pH. At this point the pH is 2 point something, and then when we titrated added sodium hydroxide at point 3.8 to 5.8, there is the when we add sodium hydroxide, there is little rise or some rise in pH. And this, when we add, first we add sodium hydroxide at the starting point, abruptly rise in the pH, but at the point 3.8 to 5.8, the rise in pH is small, and then there is again rise in pH. Then at the midpoint 3.8 to 5.8 is 4.8. This is the pK value at which half of the acid is dissociated. So form 1 is the acetic acid and form 2 is the acetate ion. At the pK, half is 50% is acetate curve of the alanine. Uh, Alanine is an amino acid. This amino acid has, when there is the pH is low, it is in form of this form and has positive charge, and then pH rises, and then it donate hydrogen ion, and this hydrogen ion carboxyl group releases hydrogen ion, converting into carboxylate ion, and then again pH rises, and then it donate an hydrogen ion from NH2 group, and at the pH 2.4 this condition predominate, and pH 9.9, this condition predominate, and in between these two positions there is condition at which there is no net charge on the amino acid, is called Vitrion condition, and it at this position amino group is positively charged, cancelled by the carboxylic negatively charged, and no net charge on this, and this point is at 6 point something, and titration curve for amino acid. So there are two reasons. Amino acid has two group which donate hydrogen ion. One is carboxyl group and other is the amino group. So two hydrogen it can take and give the hydrogen ion. So it is diprotic acid. Acetic acid is monoprotic acid and alanine is a diprotic acid. So there are two pK after giving and taking hydrogen ion, pK1 and pK2. At pK1, form number 1 and form number 2 predominate, and at this pK2, form number 3 and 2 predominate. So this is the isoelectric point where the net charge is 0. Below the isoelectric point, the amino acid are positively charged, and above the isoelectric point they are negatively charged. Below the isoelectric point pH, which is 6 point something, the amino acids are positively charged, and above the isoelectric point they are negatively charged. In form 1, form 2 and form 3, at below this is the isoelectric point, form 3 at pH approximately 6, and at that point form number 1 and form number 2 are 50-50 when we are titrated alanine and added sodium hydroxide in it, and at the start point the pH is less than 2, then it take donate hydrogen ion, and at point 6 it is Vitrion condition, isoelectric point, and at the pH above than 9.1 it give rise one proton and its condition negative charge, so its anion form predominate. So it has two pK because it has two point where it donate and take hydrogen ion. pH of an aqueous solution of an amino acid at which the molecule have no net charge. In other words, the positively charged groups are exactly balanced by the negatively charged group. For simple amino acid such as alanine, the isoelectric point is an average of the pK of the carboxyl 2.34 and ammonium 9.69 group. Thus, the isoelectric point for alanine is calculated 2.34 plus 9.69 divided by 2 is equal to 6.02. So the average of pK1 and pK2 divided by 2 is the isoelectric point where the amino acids have no net charge but have full charge. In addition, acidic or basic groups are present as side chain function. The isoelectric point is the average of the pKs of the two most similar group, giving not the carboxyl. So pK2 plus pK3 divided by 2, which is 10.75. So its pK2 is 12.9.1 and pK3 is 12.5 divided by. This is the arginine. It is the pK1 is 2.1, pK2 is 9, and pK3 is 12.5. So when we titrated the arginine amino acid, it is the basic amino acid. So here the hydrogen from the carboxyl group will be lost. So we will not consider in basic amino acid the carboxyl group hydrogen from the carboxyl group. We only take pK2 and pK3 rather than pK. In acidic amino acid we will consider the hydrogen lost from the carboxyl group, from the alpha carbon and the side chain. In the basic amino acid we will consider the hydrogen atom coming from the alpha carbon and the side chain amino group. It has two amino group, alpha group and the side chain group, alpha amino group and the side chain. So the hydrogen lost, we will not consider here the hydrogen given from the carboxylic group as pK1. We only take the pK2 and the pK3, and pK2 and pK3 8 plus 10 divided by 2, and this is the isoelectric point. Thank you very much.